So we had one out of order, which was the rules for assigning oxidation numbers. That doesn't make a lot of sense until you know what oxidation numbers are. And oxidation numbers are all made up and they don't matter. Okay, but in more detail, it's a way to indicate how electron cloud is distributed among a couple different things. So it relates to electronegativity. It very often is discussed simultaneously with charge, and people will talk about the charge as the oxidation state. If you have a +1 oxidation state or a +1 charge, you have given up 1 electron. But oxidation numbers aren't really a charge because there's not been a literal transfer of an electron. So it's sort of like a pseudo charge. We use them when we're doing formula writing and balancing equations. And we use them if we're using the stock system to name stuff. So remember how I said there were 2 systems for naming molecular compounds? The old one uses prefixes, dinitrogen trioxide, and the new one doesn't. The newer one uses oxidation numbers. So what we're going to do is we'll do a little bit of work with oxidation numbers, very little, and we'll do a little bit of work with naming things using oxidation numbers. You'll probably have 2 oxidation number problems on the test for this chapter and 1 stock system naming with oxidation numbers. You saw how big the rules are for naming oxidation numbers. If you look at the bottom again of your Ion Bible, you will notice that the second to last box, that is a very, very brief summary of the rules for using oxidation numbers. You'll have this on your test. I think for the amount of work that we do with oxidation numbers, it would be really stupid to expect you to memorize those rules. I want you to be able to use them, and these are the big ones. So that's what we'll do. Okay, so these are shown as positives and negatives, just like charges are. Remember, they're kind of like a pseudo charge. That's really the best way to describe them. If an atom is in a pure element, if it's a pure element, if you've got just iron, because remember, well, we haven't talked about this yet, metalheads walk alone. Iron is all by itself. It's not sharing electrons with anybody. It has an oxidation number of 0. Okay? So anytime you've got something all by itself, it's not sharing any electrons, it doesn't have a charge or a pseudocharge. So it's got an oxidation number of 0. The thing that is more electronegative gets the charge that it would have as an anion. So in other words, the thing that would take on additional electrons gets that as an oxidation number. So fluorine, when it's bonded to something, what charge does fluorine take on when it does form an ion? -1, yeah, 1-. So fluorine always has an oxidation number of 1-. The thing that is less electronegative, so the thing that if it was bonding ionically would tend to form a positive ion, gets the charge it would have had if it formed a positive ion in general. See rule number 3. Fluorine is always -1. Always, 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 always. We just know that. Oxygen is, well, it's always -2 except for a few exceptions. So it's generally 2-. When it's in a peroxide, that's different, and when it's in a compound with a halogen, because the halogens are so electronegative, you can actually have a positive oxidation number on oxygen, which is a terrible, terrible, horrible thing and stupid, but it's true. Hydrogen is either +1 or -1. Here are the important bits. The algebraic sum of the oxidation numbers in any compound that is neutral is equal to 0. In other words, the charges cancel out, or the pseudo-charges cancel out. If we've got a polyatomic ion, the algebraic sum is equal to the charge on the ion. Okay, that's pretty easy. And these apply to covalently bonded atoms. We can use the same rules for looking at oxidation states in ionic compounds, but it doesn't make a whole lot of sense to do that. We don't typically. So let's practice one, shall we? Okay, this is a covalently bound compound, UF6. What would that be? Name it. I'll give you a hint, uranium. Hexafluoride, uranium hexafluoride, nasty, nasty stuff. Okay, so the way I typically start these off is I write this, and the first thing you need to do is to get a handle on how to start this process. So if anything that's in that compound has a rule that's dedicated to it, that's where you start. Well, fluorine. If we look at our little summary of rules sheet here, fluorine is always, oops, let me put the subscript there, -1. And I do this sort of unique little format for the math on these. You can use it or not, but I find it useful. So there are 6 fluorines. They each have an oxidation number of -1. So the total negative oxidation state for this thing would be -6. Well, we know that this is a neutral compound. There's no charge. This is not a polyatomic ion. So whatever is here has to balance. So, x plus -6 equals 0. I mean, you can do this algebraically. Therefore, x equals 0. Well, plus 6. We move a negative. Anyway. X is 0, or x is 6. Jeez, a piezo Moser. So x equals 6. Got that. So this is +6. Well, now we have to look at how many uranium atoms we have. 1. So this charge is distributed over just 1 uranium atom. So we have a +6 divided by 1. Therefore, the oxidation number on this is +6 -1. And typically what you'll see in the book and in other places is your oxidation numbers are typically written centered over the atom that they're referencing. So it's not like a charge, but you write oxidation, or you can just write oxidation number is this, oxidation number is that. So let's look at H2SO4. H2SO4 is sulfuric acid. Let me get rid of this. We've got H2SO4. This is a slightly more complicated example because of the fact that there are 3 things here, and we have to find an oxidation number on each of them. So again, the first thing to do is to look and see if there's anything that we've got a rule to hang on. And we do. We have hydrogen. And so if hydrogen is in a compound with more electronegative elements, it has an oxidation number of +1. Well, are sulfur and oxygen more electronegative than hydrogen? Yeah, they are. Oxygen's pretty darn electronegative, so is sulfur. So this would be +1, and we have 2 of them. So there we've got a +2. Now there's a rule about oxygen as well. What's the rule about oxygen? Yeah, as long as oxygen is in anything but bonded to a halogen or a peroxide, it's got a -2. Okay, so that times 4, we have -8. Well, what we need now is something that will equal 0. So 2 minus 8 plus x equals 0. Well, we got -6 plus x equals 0. X is +6, algebraically. Good? Okay. So we know that this has got to be +6. Well, how many sulfurs do we have to distribute that +6 over? Just 1. So what we have is +1, +6, -2 for the oxidation numbers. The oxidation number is the oxidation number on the individual atom of oxygen. So it's not this -8 for oxygen. The oxidation state of oxygen here is -2. The oxidation state of sulfur is +6. Hydrogen is +1. Okay? So that's kind of important. They're not individual, not the collective negative pseudocharge. It's the pseudocharge on the individual atom. Does that make sense? You'll have a few more to practice with in the book, and you can check answers. Okay, so let's talk about naming using oxidation. Okay, this is the stock system that I referenced for molecular compounds. This is supposedly the newer way to name molecular compounds, but as I said, and this is, I mean, my information is getting dated now, but everybody I encountered who was doing college chemistry was using the prefix system. So I didn't experience a lot of this, and I haven't had any students come back and tell me that this is what they're hearing. So you should be aware of this, just in case. So we have SO2, SO3. With the prefix system, that would be what? Sulfur dioxide, sulfur trioxide. With the stock system, what you do is you assign oxidation numbers, and then you use that oxidation number the way you did a charge in like iron 2 oxide, iron 3 oxide. Okay, so how do we get that as sulfur 4 and sulfur 5 oxide? We got those through oxidation numbers. So let's do the oxidation numbers for SO2. Let me make that a darker. Sulfur 6. Did I say sulfur 5? Sorry. Okay, so for SO2, let's get the oxidation number on sulfur. Which one of those has a rule? Oxygen. Always -2 unless it's in a peroxide or bonded to a halogen. Times 2, so we have a -4 oxidation state on oxygen. To balance that algebraically to 0, we know this one's got to be +4. How many do we have to divide that over? Just 1. So we know that the sulfur here, so we have +4 - 2. That gives us sulfur 4 oxide. Okay, that gives us sulfur 4 oxide. Make sense? Guess what the oxidation state of sulfur is here? 6. So a lot of things can exist in multiple oxidation states, and you start to find the most common. Okay, we'll pick up. Fairly clear? What I'll do on your test is you'll probably have 2 things to do oxidation numbers for, and I'll ask you to name one of them using the stock system. So it's, you know, a point or 2. I want you to be familiar with it enough that if you do encounter it again, it's not a total shock. You've seen it, but we're not going to spend a lot of time with it. Chemical formulas and using them, because now you know how to write them, now you have to know how to use them. Yay! So this is how we determine the molar mass or the average molecular mass of a substance. Formula mass, doesn't matter. Of course, if it's a covalently bonded substance, it's molecular mass. If it's ionic, it's formula mass. But you can actually use formula mass more broadly. So, if you have a single molecule of H2O, we can figure out the mass of a single molecule of H2O. We can figure out the mass of a single molecule of water, and we do this by just using the molar mass of each of the things that's in it, multiplied by the number of atoms of hydrogen or oxygen. So we have 2 atoms of hydrogen, 1.01 AMUs. So the mass of the hydrogen in there is 2.02. 1 oxygen atom, 16 AMUs, 16.0 AMUs. We add those together, and that is the mass of a single water molecule. Couldn't be easier. We'll do a bunch more of these together. Oh, this is the distinction I want to make real quickly. Molecular mass versus formula mass. Molecular mass is only molecular mass if there are molecules. If there are no molecules, you can't have molecular mass. if I asked you for the molecular mass of sodium chloride, you could say, well, it doesn't have a molecular mass. There are no molecules. What we use when we're talking about ionics, and we can use it more broadly, and to be honest, everybody gets sloppy and everybody says, oh, what's the molecular mass of salt? Well, you know, table salt doesn't have a molecular mass, but you know what I mean. So, I mean, people do get sloppy. It happens. Formula mass is the more general term. So formula mass works for anything that has a chemical formula, whether it's molecular or ionic. So, you know, I try to remind myself to just always say formula mass, because then you can't screw it up. But I do. I'll slip. I'll ask you for the molecular mass of an ionic compound. I know I will. You can feel free to make fun of me when I do it. Just a little bit of formula mass practice, and we'll actually, I'm going to skip past this one and we're going to do one together. This is important. So in this chapter we work with chemical formulas, names, etc., and using chemical formulas. Next chapter we introduce chemical reactions, types, balancing, products, predicting products and activity, things like that. The chapter after that is probably my favorite chapter in the whole book. It's stoichiometry, and it's where we put together all the chapter 7 stuff and all the chapter 8 stuff into one big beautiful mathematical package. You will be able to do this in your sleep by that time. You have to. So anytime that you're handed a substance and you want to know what's the formula mass, so let's use, well, we'll start off with ammonium chloride, okay, NH4Cl. So the shorthand that I typically use, I don't really go through a factor label every time. What I tend to do is I will write down all the things I'm dealing with. I will jot down their mass. So nitrogen is 14.01, and that would be AMUs. Hydrogen is 1.01 AMUs. And chlorine is, somebody find chlorine. 35.45. You will be astounded at how many of those you know right off the top of your head by the time we get through chapter 9. Somebody will say nitrogen, you'll go, oh, 14.01. Carbon, 12.01. Really, it happens. So now I want to multiply by how many of each of these things we've got. Well, that's 1, that's 4, that's 1. And I tend to jot down my little note to myself here, 14.01, 4.04, 35.45, and then I usually just do some sort of notation to myself, 14.01 plus 4.04 plus 35.45, 53.50. I should cut myself off in terms of space here. Okay. So one formula unit of ammonium chloride has a mass of 53.50 AMUs. Okay. What about when they get a little bit hairier? What about when we have parentheses? Excellent. That's exactly where we're going next. So let's pick something really ugly because we like it. Let's do ammonium phosphate. NH4 3 times PO4. So I'm going to do the same exact thing I did for the last one. Now here's the difference. How many nitrogen do I have? I have 3 nitrogen. How many hydrogen do I have? I have 12 hydrogen. And this is where I think having the mental image of Lewis structures helps, because you can imagine for yourself oh yeah, I have 3 that look just like that. And so if you find yourself struggling, you know, literally remind yourself that, oh yeah, there are 3 of those. So if I had to count all the nitrogens, if I had to count all the hydrogens. Okay, let's get rid of those then. Okay, I have 1 phosphorus and I have 4 oxygens. And I guess I did this in reverse this time. I didn't list the molar masses first. I listed the number I had first, because this is one where that's really critical. Delightful. Okay, so nitrogen, 14.01. Hydrogen, 1.01. What's phosphorus? That's one I don't have memorized. Okay, 30.97 if we're doing 2. 16.00. Yeah, 2 decimal places is our standard. Okay, 3 times 14.01. 12.12, 30.97, and 64.00. I do actually, despite years and years of practice, I write this down still, because then if I screw something up, I can go back and I see where I made the mistake. The more of your work that is visible to not only you, but to me, the easier it is for you to identify errors and correct them. Okay, so we got a total yet? Okay, 149.12 AMUs. It's a heavier compound. Wait till we get into like the lead compounds. Okay, straightforward and easy enough. Not difficult at all. Just a skill that's actually just combining a lot of skills you've already had. And it all translates to doing molar mass. We're coming back to GMA, believe it or not. We're gonna visit GMA again. So molar mass was the mass in grams of 1 mole of a substance, and we did, 1 mole of carbon is 12.01 grams. Well, now we can look at a mole of ammonium chloride, a mole of ammonium phosphate, a mole of sodium chloride. And it's the exact same calculation we just did for formula mass. You're just now calling it molar mass, and instead of molecules or formula units, you're now talking about grams, or you're talking about moles and grams. So instead of AMUs and molecules, you're talking about moles and grams. So we'll do one of these. This is the exact same thing that we had for formula mass. I just changed all the words. So this now says mole, and this now says gram. That's literally all it is. It's the same slide. If this looks familiar, there's a reason. And that's to make a point that it's the exact same thing. Watch your units, because the units make the difference here. Okay, let's actually practice one together. Let's practice a couple of them together. We'll pick one that was on the test. Let's do iron 3 oxide, Fe2O3. Okay. What's the molar mass of Fe2O3? Is it 55.85 grams now, not AMUs? Grams. Oops. So 48.00 grams and okay, so I get 159.7 grams of iron 3 oxide in 1 mole of iron 3 oxide. So if I hand you a container that has 150 grams of iron 3 oxide in it, I've handed you almost a mole of iron 3 oxide. Yeah? 9? I see a few people who look uncomfortable with something. Same thing you did before. Only the units are different, and now you're dealing with you're dealing with compounds rather than single elements. So grams to moles to formula units. is the same as grams to moles to atoms, okay, or molecules. Formula unit can be a molecule or a ionic substance. So let's do a couple together. We'll do the first one together. How many moles are there in 100 grams of NaCl? The first thing we have to do is get our conversion factor for NaCl. So I'll flip over to here. So we want to know how many moles NaCl in 100.0 grams of NaCl. All right, let's get the molar. So we're going to set it up with our given first, same as we've always done. 100.0 grams NaCl. We know that what units in chemical have to go down below to cancel? Grams of NaCl. We want to end up in moles of NaCl, so what units in chemical go on top? Moles of NaCl. Well, we need this number. That's the conversion factor we're missing. So we do our handy little math here. 22.99. And chlorine 35.45. Okay. So we get 58.39 grams of NaCl per mole. (100) divided by that. 100 grams of NaCl is 1.7126, etc. moles of NaCl. With sig figs, how many sig figs did we have? We had 4, so we would have 1.713 moles of NaCl. Okay. These aren't hard. These are the very same thing you've done before. There are some practice problems in the text. You've got lots of problems in the homework that are good practice for this. So we're going to stop there. We didn't do, I hope it's okay with everybody, we didn't do the rest of these. What I'll do is give you the last 5 minutes. You can probably get 2 of these done on your own in the homework. And let's look at which numbers they are. And then tomorrow when you come in, you know what, I might try to do an online FIP for those. I'll do an online FIP for that. So that you have a chance to test yourself on that one. So, okay, that's it for today, and you've got plenty of practice problems.